In this video, we're going to be talking about logarithm properties as well as special cases. So just practicing logarithm expressions a little bit more in this video. Our first special case looks like this. So log base b of 1 equals 0. We could use or rewrite our logarithm expression in exponent form to help us simplify this and figure out what's going on in this property. So we start with our base and go in our circle. So you can see that we're talking about anything to the 0 power is always 1. Anything to the 0 power is 1. So if you see a problem such as this, and you're missing any one of these variables, hopefully you can quickly just fill it in without having to do any more math or having to rewrite it. If you just know that anything to the 0 power is 1, so log base of anything of 1 is always going to be 0. Here's another one. It's a pretty unique one. If you have your base of a number and those two are the exact same number, well then it looks like this in exponent form. Because anything to the first power is itself. So you'll always have two of the same number if your logarithm equation equals 1, and that is because anything to the first power is itself. Alright, let me get rid of this. We'll talk about another special case here. In general, we have three different numbers here in our expression. Just put it into exponent form. Do a little circle method here. Base b to the k power equals n. So this is what we've been working on really in this last video, talking about evaluating logs. This is really the basic property that is. And we're going to take it a step further in this one. So let's say that we have more than just one term here. So we still use the same property, but now this number right here is a binomial, and it doesn't really change anything. We still use our same method. We're going to say 5 to the second power is equal to whatever this is, right? So if we need to do that, we simplify and solve for x. Sometimes you'll see problems where they give you an expression for one of these missing terms here. If that's the case, just change the form and simplify and solve. So 5 squared is 25. And then when we solve for x, we're going to subtract 1 and divide by 3. So we get x is 8. And if we substitute and rewrite that, our expression looks like this. So instead of x, we use 8, so 3 times 8 is 24. 24 plus 1 is 25. So that is now a true logarithm expression here. 5 squared does in fact equal 25. Alright, let's keep going here. What if we have things that look like this? Oops. So in this case, we have a log expression on both sides of our equation here. And as long as the bases are the same value, then really this is similar to when we were solving for unknown exponents. And if we have the same base, we ignore the base and we just focus on the exponents and rewrite that as their own equation. That similar method can be used in this case. As long as the log expressions have the same base, we can ignore them and we just focus on these numbers. So as long as m is equal to n and our bases are the same, then this property works. Here's what a problem like that might look like. So because each of our logs have the same base, we're allowed to ignore them. And we just focus on this part of our equation. And that allows us to solve for x. But again, that only works as long as your bases for your logs are the exact same. So solve for x here, we could subtract x, and we could add 1. So we get 4x equals 8. And then divide by 4. And get x equals 2. So we can use that property to solve for something that's missing or unknown. Couple more. Sometimes you'll see log expressions as exponents. It's kind of weird, but it's possible. If that's true, here's what makes this unique. Because the base of the exponent and the base of the log are the exact same, we basically ignore all of that and we're left with our answer, which is this number right here, n. And we could also just change the form, put this in exponent form, just to give you a different idea of what this could also look like. Let's go in our circle here. We're going to write this, because this is in exponent form, we're going to rewrite it in log form. So we say log base b is equal to, log base b of n is equal to our exponent. Complete the circle, log base b of n. So changing the form there helps you see that this is why we're able to basically ignore these and just focus right here. So either in log form, which is what we just did in that last example where we saw this, or if we change that to exponent form, in which case we ignore all this and we just focus on right there. So you might see a problem that looks like this. 2 to the log base 2 of 7 power is equal to something. We don't know. Well, because the base of our exponent form is 2 and the base of the log form are 2, we ignore it and we know that our answer is just right here, 7. And if we put that over into log base form, maybe it becomes more clear. We have log base 2 of 7 is equal to log base 2 of what? Well, in order to make these two equations equal, they both need to have a 7 right there. So we get 7. Alright, one more. It's kind of similar to what we just did. This time, I'm going to say log base b of b to the k power. Well, in that case, again, we basically ignore everything but this k. So it's equal to k. Because again, bases of exponents and bases of logs are inverses of each other. They cancel each other out. And we're just left with the remainder. If we were to use are exponent form. We can see that they are truly equal. So log base b, we start with b. B to the k power equals b to the k power. So again, as long as your bases are the same, you can ignore them. And log bases cancel out exponent bases. They're inverses. So I want to use the rest of my video here to explain what I mean by inverses. Let's get our graph going here. Why are logs inverses of exponents? Let's do an exponent function here, an exponential function. So 2, let's say y equals 2 to the x power. Let's see what that looks like. Come up with an xy table. 0 and 1 first. So 2 to the 0 power is 1. So 0, 1. 1 as an exponent would be 2 to the first power, that's 2. So 1, 2 is another point on our graph. Go a little farther here. If we use an exponent of 2, we get 2 squared, that's 4. So 2, 4 is another point. And let's do one more here. 3. 2 to the third power is 8, so 3, 8 is another point on our graph. So climbing quickly, exponential growth here. Let's go one more on the other side. Let's do negative 1. Remember that a negative exponent creates a reciprocal, so that's actually the same as 1 over 2 to the first power. So negative 1 is our input, we get an output of 1/2. If we were to keep going, it would get lower and lower and lower and lower, infinitely approaching that x-axis. So there's our exponential growth function. Now let's try and graph the inverse. Use a different color here. So here is going to be our inverse xy table. Remember that when we do an inverse xy table, we basically just flip our x and y values. So we have an input of 1/2, and that gives us an output of negative 1. We're just swapping these x and y values. Input of 1 gives us an output of 0. Input of 2 gives us an output of 1. Input of 4 gives us an output of 2. And an input of 8 would give us an output of 3. Let's graph this and see what those values look like. So 1/2, negative 1, about here. 1, 0. 2, 1. 4, 2. And 8, 3. So we basically have this similar to an exponential growth, except it's going in an inverse fashion. So it's getting closer and closer to the y-axis, but never touching it, and then growing exponentially in this horizontal fashion. So that's kind of weird. And if you remember that inverse functions are always symmetrical across the y equals x graph. So there's one more color here. Y equals x. So y equals x is just a linear function with a slope of 1 over 1. So it's basically this line going diagonal. And inverses are reflections across that line. So as you can see, our exponential growth is reflected in this graph. And really, this graph is a logarithmic function. So inverses of exponential functions are logarithm functions. And that is what the graphs of each would look like. So good luck using those special patterns there, or special cases, in evaluating more logarithms.